So hi everyone, thank you for coming. So you probably have noticed from the email that we have a special episodes of two CAP seminar today, broken up in half and half, 30 minutes and 30 minutes. So first speaker, I'll give it up to my colleague Veronica to introduce him, and then we'll follow it up with the next speaker. Thank you.
All right, we got a really good one for you this Friday. All the way from Melbourne, Australia. My good buddy from grad school. He was a visiting grad student for 6 months at UCLA. They were the best 6 months. We hung out all the time. We were in the same group. And Benji, this is our speaker, Benji. He just got his degree, so he's Dr. Benji now. He has 8 first author papers. He's got an incredible grasp of astronomy and science and math, or maths, you know, he's from Australia. And he's also like really nice and cool and like talented. So I can't even like resent him. So he's just, he was a great friend to me, and we've still kept in touch, and he's gonna give a fabulous talk, I'm sure of it. So take it away, Benji.
Yeah, thank you very much for that really enthusiastic introduction. So I'm Benji. I'm going to try to live up to the hype. I'm going to tell you all about my thesis work, which is all about exploring chemical inhomogeneities in galaxies across cosmic time. So the problem I'm really interested in trying to solve is galaxy evolution. And that Wi-Fi label is just going to stay up there, it looks like. But you all know how to extract information from incomplete data, so hopefully that won't be too much of an annoying thing. But yeah, galaxy evolution. In broad scales, we know how it works. There's small overdensities in the early universe that grow to become larger dark matter overdensities in the cosmic web. And then in the densest regions of this cosmic web, we have gas accreting and collapsing to form stars. So galaxy evolution is a solved problem. That's a joke. Obviously, there's a lot that we still don't know. Specifically, we don't know about the gas physics that is really important in driving galaxy evolution. So we know that gas has to accrete into galaxies to fuel generations of future star formation, but it's still not clear whether this accretion happens smoothly or in clumps, whether it's preferred on the edges of the galaxies or in their central regions. Similarly, we know that supernovae should drive outflows in a galaxy with metal-enriched gas, but it's not clear how much of these outflows fall back into the galaxy, if at all, and how enriched they are, and what the timescales of this process are. In addition, we know that interactions between galaxies, such as mergers and stripping, are really important for driving galaxy evolution, affecting some large-scale properties of galaxies. And we also know that feedback, turbulence driven from stars exploding, is a really important feature in our galaxy models, as it's important to stop future generations of star formation and slow things down. But every different simulation has a different model for how this is supposed to work, and nobody's got a proper understanding of what's actually going on in terms of this feedback. So these are the things that we kind of want to learn. These kind of like small-scale baryonic processes that are really important for driving galaxy evolution. And so to do this, the thing that I look for is metals. And so here's a really nice periodic table that shows where each of these elements has come from as a function of cosmic time. It's a really great graph. Take the time to look at it if you want. Show it to your other friends who are interested in science. They'll stare at this for 10 minutes in wonder. But the real takeaway from this slide is that except for those first three, hydrogen, helium, lithium, every one of these stars, in every one of these elements was either formed in a star or in the products of stars. So if we're looking at where these elements are distributed in a galaxy, we can learn a lot about how these galaxies have been forming stars and evolving over their lifetimes. So to collect this information, I use integral field unit spectroscopy. And basically what this is it's a collection of fiber optic bundles pointed at a galaxy that allow you to get a spectrum at every pixel of the galaxy. So you get these data cubes where at every location you have a full wavelength, full spectrum, which you can use to extract the metallicity at every single pixel of these galaxies. And the data that we're getting out of these instruments is really great. So here's some pictures of some metallicity maps that we're getting with MUSE in the local universe. Yeah, they're stunning, right? So you can see in this one on the left, for example, there is evidence of a metallicity gradient in this galaxy, more metals on the middle, less metals on the outside. But in addition to that, there's all of these small-scale fluctuations in metallicity, little bumps in regions where it locally deviates from this metallicity gradient. And all of these signatures of these small-scale astrophysical processes that we're trying to probe. So that's kind of the work that I'm doing, is trying to analyze this data and get as much information out of it as possible, both with this really high-res stuff, and also some lower res stuff in the distant universe. So this is a recent metallicity map captured by James Webb. It doesn't look as pretty and fancy until I tell you that this is a map at redshift 3. So really great effort, and you can see that in this galaxy, there are also like deviations from a standard chemical gradient profile, large asymmetries in the metallicity profile that we want to capture to kind of like get a handle on the physics that's in play at these galaxies. So in my talk, I'm going to be talking about how I do this, how I connect this really nice data to theories of the ISM structure, both with really nice high-resolution data in the local universe, with not so nice data in kind of like cosmic noon, and also finding evidence of chemical inhomogeneities in galaxies where we have no resolution at all. But before I talk about that, I'm going to start with the nicest data that we have when we've got data with resolutions below about 200 parsecs per pixel. And for that, the tool that I am bringing to astronomy to analyze these galaxies is geostatistics. So what is geostatistics and why have you never heard of it? It's not because I made it up. I would have named it something much cooler. Instead, it was invented by a bunch of French mathematicians working in South Africa during the gold rush. So they were trying to answer questions like, if we dig up a lot of gold over here and not much gold over there, where do we dig next to maximize the amount of gold that we get? So building up these probabilistic models of stochastic processes that are correlated over a spatial domain. Now, it turns out if you replace gold with metals and gold fields with galaxies, the maths doesn't know, and so you can use these same families of modeling techniques to get really informative, two-dimensional predictive models of the metallicity distribution of galaxies. So how do these models work? Basically, it's a hierarchical model. So the first split we make isn't too novel. We say that the metallicity we observe at each location X is a combination of two parts. It's the true metallicity, but it's not exactly the true metallicity. There's also going to be some observational error associated with that measurement. But if we know the properties of our telescope, we know how bright our emission lines are, we can get some estimate for how we expect this error to statistically behave. The second split we make is a bit more novel. We say that the metallicity at each location comes from two parts. There's the mean metallicity that you'd expect at each location, which can come from a metallicity gradient model. But then on top of that, you expect that not every point in the galaxy should have a metallicity that's exactly on its mean. Excuse me. You expect some level of random fluctuations just because star formation is a random process, turbulent mixing is a random process. So in addition to this metallicity gradient, we expect some sort of random fluctuations to be present as a signal on top of this with some sort of spatial correlated structure. So that's the game that we're kind of trying to do with this metallicity geostatistical modeling. If we can model how the error behaves, what the large-scale gradient is, and how these small-scale fluctuations are going to behave, then we can make a really nice predictive model for our galaxies. So when you're doing this, one challenge is how do we separate the small features from the noise in our model? Luckily, geostatistics has a tool that can help us, which is the semivariogram, which is a plot of variance against the separation that lets you separate spatially correlated and uncorrelated sources of error around a mean trend. And to kind of illustrate how this works without going into too much maths, I've prepared a worked example. So on the top row, we have 3 different random fields, and on the bottom row, we have the semivarograms that are associated with each of them. So in this first field on the far left, we just have white noise. There is no spatial correlation between any different points in this image. And so when we look at the variance between 2 pixels, it's going to be constant regardless of how far they're separated from each other. So when we plot the semivariogram, we get the same variance at each locations. We get a flat line. In this second image, instead I've got a really highly correlated random field here. And so you can see that if you look for 2 points that are close to each other, there's going to be a lot smaller variance in their metallicity than if you look at 2 points that are further away. And so what you see from the semivariogram is a sort of graph that sort of builds up as you go further and further in separation. Your variance kind of increases until a point. And that point tells you the scale of the largest fluctuations in your data. You can also look at the height of this graph to figure out what's the amplitude of these fluctuations. How much variance is there? So you get all of these details about chemical mixing going on in these galaxies. In this third map, I've actually done something a bit cheeky, which is just added these 2 maps together. And so now you've got the correlation signal there, but it's a bit buried. It's much harder to see. Luckily, with the semivariogram, because variance is an additive property, the semivariogram for this final one is just going to be the sums of the semivariograms of these other 2, the sum of the variance of each separation. And what's really nice about this method is that when you take a function that's really informative and you add a constant to it, you get the same really informative function, just shifted up. So with this technique, from this final graph, we can still extract all of the information about the size and spatial scale of these random fluctuations as if there was no noise there at all. which is a neat mathematical trick. Unfortunately, it would never work on real data, except here it is on some real data. And you can see that it works great. You can find the scale of these fluctuations. You can find out how much variance there is. The semivariogram a really informative structure. It gives you the same amount of information that a power spectrum does, and there's some mathematical transformations you could do to go from a power spectrum to a semivariogram. Ask me about this if you want. I've got a paper that's kind of like showing you how to do that. One nice thing about the semivariogram as well is that it's really good at handling bad data, so data with missing pixels or edge effects, where a power spectrum is a little bit less reliable. So what can we use these data structures for? Basically, we can reveal sort of like what the small scale structure of the variance in metallicity is, and we can fit a model to that. And then once we've got a model, we can compare it to analytical theories and simulations. So in this first project that I did, I tested an analytical model devised by Krumholtz and Ting. It's powered by stochastic partial differential equations, but rather go into them all, I thought I'd list you the assumptions and then show you a simulation of how this looks. So I took all the physics, put it in a box, and what you're seeing here, each of these yellow spots is a supernova that is releasing metals and enriching the ISM. And then over time, these metals diffuse just into the galaxy, just through linear diffusion. And so what comes out of this model over time is there's a small buildup of metals in specific regions based on where star formation is happening. And so what you can get from this formalism is an estimate on what you expect this spatial correlation structure of these metallicities to be. Now we can measure this in the galaxies, we can compare our models to the theories, and what we find, at first glance, it looks like it's a pretty good match between the theory and the model, until I tell you that the model that we tested is the green line, and the red line is that model expanded up by a constant factor. So to get a match to the variance structure that I'm seeing, the scale is pretty good, but the amount of variance in these galaxies is underpredicted by this model by a factor of about 1,000. Here's the same result for 6 other galaxies, so you know that I'm not cherry picking. In each case, I had to scale it up by a factor of 1,000 to 10,000. And what this means is that basically these galaxies are really not very well mixed. They're not as well mixed as our models were predicting. They've got these large inhomogeneities of the scale of 0.1 dex that wasn't expected to be there. So right now I'm doing some work with a master's student who I'm informally co-supervising Tree to look at the fire simulations, looking at some really nice zoom-in simulations of galaxies, constructing semivarograms for them, and trying to test some more detailed models of the ISM to see if they match data. So, yeah, another thing you can do with this geostatistical method is use it to construct predictive models of the ISMs of galaxies. So when you observe the metallicity distribution of a galaxy, you can only get the metallicity at specific H2 regions. So if you want to figure out the metallicity at a location outside of those H2 regions, one of the black points in this graph, the traditional way to do it is to construct a metallicity gradient model. And this gives you a picture of the galaxy that looks like this. There's more metals on the middle, there's less metals on the outside, but there's a lot of details in this high-resolution data that are being lost when you do this method. On the other hand, when you use a geostatistical model, you can account for these small-scale fluctuations, and this gives you a picture of the galaxy that looks a lot more like this. So there's still more metals on the middle, there's still less metals on the outside, but there's all of these details of galaxy evolution that are showing up now, all these little local patches of metal enrichment that might be signs of recent star formation that hasn't mixed in yet. There's a point over here, which is a low metallicity point, which might be a sign of recent gas inflowing into this galaxy. All these details on the small-scale physics of the ISMs that we're really trying to capture with these models. So these models are really good at making predictions of the metallicities of galaxies. So to test this out, I took away 10% of my H2 regions, trained these models on the other 90% of the data, and then used that to predict the metallicities of these H2 regions that I hadn't fit. I repeated that 10 times for all the H2 regions. And for the metallicity gradient method, I got a fairly good agreement between the data and the models, but there's a bit of regression to the mean. Specifically, the metallicity of low metallicity points is overestimated. The metallicity of high metallicity points gets underestimated. On the other hand, when you account for these local fluctuations that you can fit the form of, you get a much better agreement between models and data, even for these low metallicity outliers over here. So the final thing that I wanted to do kind of like with this geostatistics study was figure out what resolution data do we need in order to get the gains from these new methods. So it works on the really nice, really high-res data that's coming out of Muse, but does it work on galaxies like Khalifa, Manga, Sami, the kind of like kiloparsec scale resolution IFU surveys? So what I did was kind of like took my really nice data cube and binned it, made it worse and worse and worse, and tried it with the same family of techniques to see if I could still get good predictions and good analysis of kind of like the small scale structure of the ISMs for these galaxies. And what I found was basically for these galaxies over here, I got a consistent reading of the correlation scale for these galaxies. So what that means is sort of like you can use these techniques with galaxies with resolutions of up to a couple of hundred parsecs per pixel, roughly. Which is a really nice opportunity because there's a lot of galaxies that have been surveyed in the local universe which have ISMs that have a resolution of 200 parsecs per pixel or finer, which means that we can expand this analysis to a huge range of galaxies with different morphologies, masses, star formation profiles to kind of like look for links between the small scale structures of the ISMs, the small scale physics, and the galaxy's larger scale properties. So that's work I'm excited to be doing in the future. Now, at this point, you're probably wondering, okay, well, this is great, but what if my data is too coarse? What if it's not 200 parsecs per pixel, but is about a kiloparsec? Specifically, I'm interested in modeling data that looks like this. So these are a bunch of galaxies with metallicity maps from about cosmic noon that are really popular in the literature because they have these inverted metallicity gradients. In reality, they have really chaotic metallicity profiles with lots of features of asymmetric processes that are probing like gas physics that's going on in these galaxies. So to analyze data like this, I worked with Tommaso Trio and a few members out of UCLA to develop an extension to the forward modeling program Lenstronomy. And so what this does is it kind of like takes a two-dimensional metallicity map of a galaxy and it accounts for PSF smearing, pixelization, and observational noise to give you a realistic data product that you can then compare directly to your observations. So this is really good at a couple of things. First of all, when you have point spread smearing, that can flatten the metallicity gradients that you measure with a normal method. However, when you use more forward modeling to account for this PSF smearing, you get a much better agreement between the recovered metallicity gradient and the data, even when the PSF is quite large. And then the second thing you can do with Lenstronomy is that you're also able to fit two-dimensional models to the metallicity distribution of galaxies that account for asymmetries that you can see in the data. So not just fitting metallicity gradients anymore, but fitting like these predictive two-dimensional metallicity models that can capture large-scale features of galaxy physics. And this is ongoing work that I'm currently contributing to with the James Webb Glass collaboration as well. So looking at some lensed galaxies of Able 2744, hopefully to quantify their ISM soon. Now, in the final part of the talk, I'm going to talk about what you can do for high redshift galaxies where you don't have resolved metallicity maps, but you still want to be able to see signatures of chemical inhomogeneity. So how can this be done? It seems a bit hard. If you don't have the resolution, how can you see that there's chemical inhomogeneities in the galaxy? So basically, when you take the spectra of a galaxy, what you're kind of doing is you're taking all of the light from a galaxy and you're putting it into one bucket. And you're saying overall, over this entire galaxy, what fraction of its mass is heavier than helium versus the total mass fraction of the galaxy. So this is emission spectroscopy. Another thing you can do is if you could measure the metallicity at a specific region of a galaxy, so not a bucket anymore, but an eyedropper, you can get the metallicity at that specific region. Now, if a galaxy is perfectly chemically homogeneous and well mixed, these two things should agree. But if there's any disagreement between them, that's evidence of chemical inhomogeneities in your galaxies. So what can we use as a cosmic eyedropper? Turns out the answer is gamma ray bursts. So these are super bright, super luminous explosions that outshine their galaxy by a factor of 1,000,000. You've got all the energy of a supernova collapsing and being channeled into one narrow beam. One thing you need to know about gamma ray bursts is they're supposed to come from really high mass, really low metallicity progenitor stars. So this biases their formation to low metallicity regions of the galaxy. But what this kind of means is that with a galaxy, from its absorption spectrum of its afterglow, you can get the metallicity at a specific point of the galaxy along its line of sight coming to you. So I'll be calling this the absorption metallicity from a gamma ray burst, and I'll be comparing that to the emission metallicity that uses light from the galaxy itself. So now, when you've got these two metallicity measurements, the first most natural question to ask is, should they agree with each other? So to test this out, I turn to the illustrious TNG simulation. And this is a large volume hydrodynamical cosmological simulation with a full suite of baryonic physics. So using this simulation, at each redshift, I selected a few galaxies to be gamma ray burst hosts, put some gamma ray bursts in them, looked along the line of sight to get the line of sight average metallicity to us, and compared that to the overall light-weighted emission line metallicity for these galaxies. So using a few thousand galaxies at a couple of different redshifts, I constructed this prediction. So this shows that the emission and absorption metallicity of these galaxies in general should not agree. at low metallicities, you have a pretty good agreement, but as you go to higher metallicities, the metallicity from the site of the gamma ray burst is often lower than the overall metallicity of the galaxy, which is sort of what you expect. So then the next thing I decided to do was look at 3 different cosmological simulations. So all of these simulations were designed to do the same thing, make realistic populations of galaxies throughout cosmic time, but they differ in the small-scale assumptions for the subgrid physics that's going on in these models. So based on that, I wanted to see, do they all have the same kind of inhomogeneous ISMs, and do they all predict the same structure between the relationships between emission and absorption metallicity for gamma ray bursts? What I found is yes and no. Qualitatively, they all agree that metallicities, absorption metallicity should be lower than emission metallicities, but quantitatively, they all have very different shapes, which means that hopefully with enough observations, we can start distinguishing between them. Now, this magenta cross on the plots was the first gamma ray burst host galaxy for which both absorption and emission metallicities were measured. But since the time of writing this paper, a lot of more data has come out using the James Webb program. And from that, we can populate this plot with a lot more points that show the locations of gamma ray bursts with absorption and emission spectra. And so now with this population of 10 data points, we can sort of say maybe there's some marginal evidence for preferring the TNG models of ISM physics over these other simulations. But this is still early work, and I haven't done the statistical analysis on this yet. But one thing that this means is that from our evidence, these chemical inhomogeneities are not just present in local galaxies, but also at galaxies up to cosmic noon and even beyond. And that is really important because it has big implications for the rates of transients that we see. So it implies different things for the rates of gamma ray bursts, but specifically I want to also talk about some pair instability supernovae. So these are supernovae. No one's observed one yet, but they're rumored to come from the most massive, most metal-poor stars. And in general, people think that this limits their production to the early universe. However, what I've shown in my research is that when you account for the chemical variations within these galaxies, you realize that these pair instability supernovae progenitor stars can be present much down to much lower redshifts than you might expect, which has great implications for how observable they will be with future surveys. So to test this out, I made some simulations of the observability fraction of pair instability supernovae using 2 different telescopes. Firstly, using the Hypersub PrimeCam mission, which is an archival survey that ran from 2012 to 2016, and also using predictions for the Euclid Deep Survey, which has just begun observing. And so what I found, when you account for metallicity inhomogeneities in galaxies, with Hypersub PrimeCam, the expected number of pair instability supernovae that you should be able to see is 0.03, which is very in line with the 0 that we've observed, so great job, good prediction. On the other hand, when we use Euclid, accounting for chemical variations in galaxies, the expected number of pair instability supernovae over its lifetime is 83. Over a 6-year lifetime, and that's an order of magnitude greater than the 7 that you might expect if you assume that galaxies are chemically homogeneous everywhere. So that's all that I kind of wanted to talk about. So for really nice high-resolution data, geostatistical methods are the way to go to extract the maximal information and learn about the small-scale properties of the ISM. For data where you don't quite have the resolution, Lenstronomy's metal modeling package is a really good tool to be able to correct for PSF smear and fit asymmetrical models of the ISMs of galaxies. And finally, these kind of findings that galaxies are not chemically homogeneous everywhere has great implications for the rates and host galaxies of transients such as gamma ray bursts and pair instability supernovae. So thanks for your time, thanks for paying attention, and I'll take any questions.
Oh, okay. So for the geostatistical methods that you apply, is this a post-processing thing, or is this something that you do on the fly? Or you just get the FAR simulations and then you post-process, or do you?
So for the geostatistics part of things?
Yeah.
Yeah, I take simulations and I kind of look at their output. So for simulations, I'm making kind of mock IFU observations and then comparing that to real data.
So you get the simulations that are already done, and then you do a post-processing on top of them. Okay. Yeah. Thank you. Awesome.
Yeah, thank you for the talk. So I was curious when you were talking about your first project where you were under-predicting sort of the clumpiness of metallicity in the ISM. You said that you had modeled that with uniform star formation, right? are you taking into account, do you think that some of that is due to the clumpiness of star formation in the ISM, or do you think some of it is more ISM physics? What do you think is dominating that?
Yeah, it's really interesting. I haven't done a geostatistical analysis on star formation rate. I think it'd be really interesting to do that. This signal is kind of like a bit, how much of it is clumpiness in the star formation and how much of it is kind of like telling us physics about metal diffusions and stuff. I think it's still unclear. I think we do have the data and I do have the method, so it's something that we can test.
But I didn't really understand. So how do you set your scaling? Is there a prior information how much you need to do the scaling, or you take the information of your variance already and then apply the scaling? Because do you have beforehand information already? How do you know how much to scale?
Right, so we kind of like learn the covariance structure from the data, and then we compare that to the models that we fit, and we basically find that the models that we fit don't match what we see in the data. And so then I'm just multiplying the amount of variance in those models by a constant factor.